You could write this as I root mean square root 2 sine of 2 pi ft. And then you would rewrite this as sine of 2 pi ft plus pi over 2. It doesn't matter which one is the 0. What matters is the relationship between them. Whatever phase angle this is, this one is ahead by pi over 2. Or if that's 0, this is negative pi over 2. And it's borne out by the picture here. The current is behind. It reaches its max later than the source voltage or the inductor voltage. Okay? Okay, now let's go to the actual numbers. In a few minutes, when we do the capacitor, then I'm going to talk about what phasors are. And we can visualize this with phasors. Okay? So let's actually calculate some measurable quantities so that we can now check. What should the current in the circuit be? If I put an ammeter. The ammeter is going to measure the root mean square current, right? So that one is the 6.57 over 2 pi times 60, because we're using a regular source here. It's 60, and then the inductor, remember, was 9.5 millihenries. Okay, so calculate all that. Let's see what we get, and then we'll check it. Okay, so the current should be 1.83 amps. Now, sometimes when we have the inductor by itself, we noticed this earlier the other time. Things don't work out that well because the inductor has its own internal resistance, right? So if it doesn't work out, don't throw stones at me or whatever. Okay? So the current that I'm getting here is 0.055 amps. So way, way different, huh? Hold on. Sorry. I have it connected right to the... Yeah, there you go. So I had it connected with a resistor in the circuit. So that's in a minute. So no resistor now, just the inductor. The current is 0.326 amps. 0.326 amps. So it is less than the current predicted by that. Therefore, there's an internal resistance. Now, I've also got the oscilloscope hooked up across the inductor, and you should see it should have the same voltage as the source voltage because there's nothing else, in this circuit. So if I measure the amplitude from bottom to top, 3.5 divisions or 3.4 divisions, 3.4 times 5 volts per division. This is the scale, 5 volts per division. So 3.4 from the bottom to the top 3.4 divs times 5 volt per div. That gives you the total amplitude, right? That's 17 volts. Divide that by 2, you get 8.5 volts. Divide that by root 2, right? Because that's the root mean square. That should give you 6.57. That's it. And then if we do the period again, it's the horizontal number of divisions. One, two, three, 3.4 times 5 milliseconds. So is that, what is that? That's it? 6? So it's a little bit off. But this one, I wasn't quite sure if it was 3.4 divs or 3.5. So if I'd maybe made a little more accurate determination of that, that could have been a little bit better. But it should be 6.57. And then the period is the period between the peaks. I think I said 3.4. That one's also 3.4 div. 1, 2, 3, 3.4. And then the, hold on, let's see. We should calibrate this so that it's on the calibrated scale. (3.4 times 5 milliseconds). (17 milliseconds). Okay. And then since the frequency is 60, 1 over 60 is 0.017. Yeah, so that one works out perfectly. So 17 milliseconds. So the period works out, the amplitude works out. Okay, now